All right, now we are recording, and now I will share the document cam screen. All right, problem set number 7 is all qualitative, so there's no calculations at all today. It's just checking your understanding of the different modes of heat transfer that we're going to talk about sequentially over the next, actually kind of 4 days, because the fourth day is combined modes of heat transfer. So today we'll talk about conduction. Next time, convection, after that, radiation, and then after that, combined modes of heat transfer. So this is just kind of checking your qualitative understanding of modes of heat transfer. So the first one, I probably was literally thinking of my mug of hot coffee that I have every morning. So I got this mug of hot coffee, and the first one is, what type of heat transfer is probably occurring at the surface of the coffee? So it's a hot liquid, and the air in my office is relatively cool. So what kind of heat transfer is happening? Probably convection, specifically probably natural convection, because the hot coffee is warming up the air directly above it, and then that air becomes less dense and it rises, and then cold air fills in that gap, the void where it was, and then it just forms this complete loop. So probably natural or free convection is the best answer to part A. Part B, what type of heat transfer is probably occurring between the coffee itself and the interior sides of the mug? All right, well, that kind of depends on if it's just sitting there or if I'm stirring it or if there is maybe some natural convection inside the coffee itself, because it's a liquid and it has it's transferring heat to the walls, probably via natural convection. So some type of it could be conduction, I guess you could argue, if the coffee is totally perfectly still, but most likely I would say it's probably some type of convection. So either natural convection if I'm not stirring it, or else forced convection if I am stirring it with a spoon. I used to add a bunch of sugar to my coffee in the mornings, but I've gotten away from that. So added sugar is not good for you. So there's debates about whether coffee itself is good for you or not. But anyway, I thought maybe I should get away from added sugar. So anyway, I don't stir it very much anymore. But if I did, that would be forced convection. Part C, what type of heat transfer is probably occurring between the sides of the mug and the surrounding air? You know what the next question should have been? The next question should have been, what type of heat transfer is occurring between the interior sides of the mug and the exterior side of the mug? That's probably the next logical question, and that would be conduction. You got conduction through this solid right here. It's not moving, so it's not convection, and it's a solid. We're not going to have radiation through an opaque solid like this. So just conduction through the wall of the mug, from the interior to the exterior wall of the mug. And then part C, what type of heat transfer is occurring between the sides of the mug and the surrounding air? Well, once again, that would probably be some type of convection. If we say that the air in my office is still, it's pretty still, then we could say it might be conduction, but most likely you got some type of convection, either natural convection as the hot, it's pretty warm, the side of the mug is pretty warm, so it warms up the air, the warm air is less dense, so it rises, it's buoyant, so then it creates this circulation. Or you could actually say, I've got some vents in the ceiling of my office, so there is some small amount of forced convection, but some type of convection probably is the best answer for part C. And part D, what type of heat transfer is occurring between the mug and the walls of the room? All right, well, there's probably two things that are significant here. We do still have convection, so probably we got convection from the side of the mug to the air, and then that air is moving either through natural convection or forced convection, and then it's transferring its heat to the walls. So there probably is some amount of heat transfer through some type of convection through the movement of the air in my office. And then there's also probably some radiation. There's some radiation, which is a direct heat transfer from in the infrared spectrum. So a direct heat transfer in the infrared spectrum from the side of the mug to the walls itself. All right, so that's part D. Let's see if I said all these correctly. So for part A, we had natural or free convection. For part B, I said conduction if the coffee is still, or natural convection if it's moving. For part C, I said natural convection. So I guess I assumed here that there was no ventilation. That's fine. You could argue either way. That's fine. These are qualitative and a little bit subjective as to what is the most significant mode of heat transfer. Part D, what is occurring between the mug and the walls of the room? We've got some radiation, probably also some convection as well. Okay, that was number one. Number two, water and iron have these properties for specific heat capacity and for thermal conductivity. And remember, I said last time that electrical conductivity is closely related to thermal conductivity. It doesn't seem like it would be, but they actually use the same mechanisms. It's the motion of electrons, the mobility of electrons that allows a material to transfer charge via current, as well as transfer thermal energy as well. So part A, if you wanted to build a trom wall, which is a thermal energy storage device, inside your house, which material would you choose, iron or water? Well, you want to choose the one that can store the most energy. And the parameter that measures the amount of energy it can store, equivalently the amount of energy that it takes to increase the temperature of the material by a certain amount, that's specific heat capacity. So you'd be better off making a trom wall primarily out of water. I mean, you got to have something to hold the water, but primarily if you had your trom wall made out of water, that'd be a good choice because water can hold a lot of energy. It has a very high specific heat capacity, as you can see, compared to iron. Part B, which would work better to conduct heat away from a hot surface? So there we're going for the one with the highest thermal conductivity, which you can clearly see is iron. Iron has a much higher thermal conductivity than water would be. So you know how when you jump in a pool, it feels cold oftentimes. Even if the water is the same temperature as the air, the water feels cold because water has a higher thermal conductivity than air does, and so it wicks away your body heat more quickly and more easily. So just imagine, I mean, it's kind of hard to imagine, but just imagine the difference here. If you somehow could swim in a pool of iron, probably don't want to do that. You'd probably get burned pretty badly. But if somehow you could swim in a pool of iron, that would wick away your body heat even faster. Of course, at those temperatures, it has to be really hot for the iron to be liquid for that to even make sense. But I'm just saying that clearly iron has a much higher thermal conductivity than water does. So that's the answer in B. And then for part C, which material would you expect to have a higher electrical conductivity? Like I said, it's the same mechanism as thermal conductivity. So you would expect iron to have a much higher electrical conductivity than water. And that's true. You can probably say that intuitively as well. Okay, that's number 2. And then number 3 says we've got this heat exchanger. We'll talk about heat exchangers in a couple of weeks. This looks to me kind of like a condenser. This is probably a condenser. So we've got some fluid flowing through these tubes, and then we've got another fluid flowing down over and around those tubes. And we want to design the parameters of this heat exchanger so that we get as much heat transfer as we possibly can between the two fluids. So using the equations that I gave you, not doing any calculations, but just using the equations that I gave you in the video on Monday for conduction, convection, and radiation, you can say some things about what parameters would be important here for a heat exchanger. So some of the ones that would be important, well, we're transferring heat through the outer part of the tubes. We're through the tubes. So it would help if we had a high thermal conductivity of the tube material itself, so we can transfer thermal energy via conduction through it. We also want to increase the surface area of the tubes to give ourselves as much area through which to transfer heat. So you want a high surface area of the tubes. And if you do the calculations, you'll find out that you can get a higher surface area by having lots of small tubes as compared to a few large diameter tubes. Much better to have lots of small tubes, narrow, small diameter tubes. We'd also get more heat transfer if we had a high delta T. So if we could use a really cold, if we're trying to cool the liquid down, like let's say we're trying to cool down fluid 2, well then we should try to use a fluid 1 that is as cold as possible to get us a large delta T between these to get as much heat transferred as possible. Also, a high fluid flow rate is going to increase our convection heat transfer coefficient. And we haven't talked a whole lot about that yet, but we will next week on Monday. And thin-walled tubes, if you look at the conduction equation, there's a delta X. That's the thickness of the tubes. So a thinner tube is going to allow for greater conduction heat transfer. And if we can get a phase change to happen, boiling or condensation, then that's going to increase our convection heat transfer coefficient, script H, even more. And lastly, for radiation, if we can use a high emissivity, that's what that means, high emissivity material, that's going to maximize the amount of radiation heat transfer that we could possibly get from, say, the outer wall of the tube to the fluid that's going over it. So that would probably be a pretty small effect, but could be something. All right, so those are all the answers to problem set number 7. I will stop